Hi, welcome back. We're here to do a video quick about implicit differentiation. Alright, so what is implicit differentiation? Well, let's take a look at some reasons why we use implicit differentiation. One, when we're going to take the derivative of something where there's an x, you'll notice that the dx is the derivative with respect to x, means that the variables agree. So derivative with respect to x, and there's an x in the expression. So when the variables agree, we have no problem. Now, in some cases, we want to take the derivative of a function or an expression that has a mixture of x's and y's. Maybe we can't get all the y's factored out completely, or something to where we want to solve for just one y and take everything with respect to x. And sometimes it's more complicated to do that. So we can just differentiate both sides of the equation with respect to x and y, and just make sure we have the correct notation. So you'll notice that when we want to take the derivative with respect to x, but there's a y there, maybe y cubed or something, the variables disagree. So when that happens, since they disagree, the chain rule must be utilized, and thus dy dx is kind of created in that stance, or used to symbolize the fact that the chain rule needed to be applied. So multiply do all y derivatives. So anytime we have a derivative with respect to x, but there's a y, in order for us to account for that, we're going to put dy dx and multiply that next to that term. Okay, so here are some strategies. One strategy, the first thing, maybe some steps you want to consider in doing this, is differentiate all terms with respect to x's and y's. Your normal x process will work, and now y's we just have to add something, or multiply, I should say, to that. Multiply dy dx to any term where the derivative of y is taken. Now, all the rules apply. Power rule, product rule, quotient rule, chain rule, anything. Those are all stay the same. And even though you have a y involved, we will use the power rule, we will use product rule, anything else that we did before. So that's all well and good. Then step 3, after we have taken the derivative with respect to any y's and multiplied that term by dy dx, then we simplify and algebraically manipulate the equation so that all dy dx are on the same side of the equation. Then we factor out the dy dx, and we simply solve for the dy dx. And that's what they're asking us to do in most of these situations. So let's see here. Example number 1. We have, it says solve, example number 1, it says solve for dy dx given y cubed plus y squared minus 2x cubed equals 4. Alright, so we notice here that this is a y, so what did the strategy say? Take the derivative with respect to y, just like you would any x. We use the power rule. The 3 comes down. We reduce the power of the 3 to 2. And then multiply the term by dy dx. We go to the next term. Bring the 2 down. The power rule applies. That's 2y. We reduce the power to 1, so we get 2y times dy dx. Minus, well, 2x cubed is 3 times 2 is 6. Reduce the power, 6x squared. And the derivative of any constant is 0. So what did we do? We found the first derivative. Next, we want to move everything that is not associated with the dy dx, or unsimilar to dy dx. Collect like terms, in other words, on one side of the equation, just like you would in any algebra move. 3y squared dy dx plus 2y dy dx is equal to, move this 6 across, and we get 6x squared. So all dy dx on one side. Then we're going to factor out the dy dx. So now we've got 3y squared plus 2y. The quantity of that is equal to 6x squared. Finally, divide each side by 3y squared plus 2y, the green, and that way we'll get our final answer of dy dx is equal to 6x squared divided by 3y squared plus 2y. So we divided there as our last step. All right, let's look at example number 2. We have x cubed plus 2x squared y plus y squared is equal to 7. Now, the first term is just with respect to x. So we bring the 3x down, we get 3x squared. Now we notice here, though, that we've got x squared times y. So, well, what do? We apply the product rule in this case, okay? Now what I like to do is I like to move the 2 away and start my product rule in here, and then I'll redistribute that 2 later. Otherwise it can get a little confusing when it's wrapped up with the derivative of each. So, again, product rule is f of x times g prime of x plus g of x times f prime of x. So let's start with f of x. Well, that's just x squared. I labeled each one f and g. So 2 again is on the outside. F is our x squared, and g will be our y. So the derivative of y is just 1 times dy dx plus g, which is just y, and then the derivative of x squared. Remember, I took the 2 away. So now if you had kept the 2, then it might be 4x, but I decided to keep the 2 outside, right? I did just the x and left the 2 on the outside, so it's just 2x. Quantity, put that in quantity, so, and then what I'll do later is I will redistribute that 2. Then we get plus 2y dy dx, the derivative of y squared, 2y, and equals 0. Now I will redistribute this 2. So if I redistribute the 2 to here, there, and then there, I get 3x squared plus 2x squared dy dx, bring this dy dx in, plus 2 times 2, which is 4xy. Now no dy dx there because I didn't take the derivative of y. I just replaced y. It was g. So plus 2y dy dx. And now I color-coded this so that I know my dy dx's are in blue. Everything else that's not associated with the dy dx can go to the other side of the equation. So I collect my like terms, 2x squared plus 2y dy dx. Factor out a dy dx, and that will equal, well, when I moved 3x squared, I had to subtract it and move it over to the other side, as well as this 4xy. Subtract it from both sides of the equation, and that ends up right there. Now, once I factor out a dy dx, I get a quantity 2x squared plus 2y, and that equals negative 3x squared minus 4xy. So for a final result, what I can do is divide, right? Divide 2x squared plus 2y, and we get dy dx. We isolate dy dx by itself, and that means that we have our final solution. So what do? We did the power and the product rule. Then we distributed. Then we simplified and used some algebra to isolate, start to collect like terms. Then we went to factoring, and then we divided and we got our solution. So anyway, that is implicit differentiation. Practice it, enjoy it. It's a great time. It's calculus. It's fun. It's wonderful. Yahoo.